We are looking at the f of ax, which is a horizontal compression on the function f of x. And we're going to look at what does this do to the graph of the function and what does this do to the derivative. So we're looking at an example here of y equals sine x. So this is a sine x graph that we have here. And we're going to see what happens when we do a horizontal compression of sine 3x. So that 3 represents a horizontal compression of times 3, or 1/3. So we've got in here in blue the 3 sine of 3x graph, and in red we have the original sine x function. So if I take some reference points here, there's my vertex, and I can see that that vertex has been horizontally compressed in this direction towards the x-axis by 1/3. Okay, so what happens to the graph? In general, if you take a look at the blue graph compared to the red one, the blue graph looks like it's 3 times steeper, right? The blue looks like it's 3 times steeper. And in fact, it is. And why is that the case? Okay, so if I take a look at a triangle and I just draw some random triangle, and I make this, if I do a horizontal compression on this graph, if we take a look at the triangle, a horizontal compression is going to make that graph steeper. So if I start with my original function here and make my run 3 times less, then that means that the slope becomes 3 times more. So this is a generalization I can make with my graphs here. So when I do this, when I do the derivative then, the derivative, since its slope is going to be affected the same way. So when I differentiate with an inside horizontal compression of 3x, what I can do is I can account for that horizontal compression by multiplying the slope function, or the derivative, by times 3. And that accounts for a 3 times greater slope at any point x. And this actually can be generalized for every function. So if I want to take the derivative of f of ax, then I can just differentiate normally the outside function, and I can apply the times a from the inside. And that accounts for the horizontal compression of a. It just makes the graph a times steeper. So we're going to deal with this inside times a little bit differently later on when we learn the chain rule. But for now, if we see a horizontal compression, we can just think of it as the slope, the run getting 3 times or 2 times or whatever times smaller, which then will affect the slope by making it that many times bigger. Okay, so we times that slope by that factor. So an example here is if I differentiate that y function, the derivative of y is going to be 1 over 4x. So 1 over x is my derivative. I need to bring the 4 with me. But then, because of that extra times 4 here, I'm going to make that 4 times bigger by timesing by 4. And so what ends up happening is my derivative simplifies to y prime equals 1 over x. Okay, so there's my derivative, and that's how I accommodate the horizontal compression. But you may have noticed that in this particular function, and this is it's in this log function only, that this log of 4x is same as log x. Now, why is that the case? Well, if I actually apply some log properties here, I can rewrite this function as log 4 plus log x. And that horizontal compression of 4 can show up on the outside, and this really is just a number. We've now just shown this as a number. In fact, if we think of it in terms of transformation, it's just a vertical shift. And we know that vertical shifts, or constants, differentiate to 0. So if I actually differentiate this, notice that y prime equals, that differentiates to 0 plus 1 over x. I actually get the same thing. So we could do it as using log properties, or we can do it using a horizontal compression of 4 and times by 4, but in either case, we get the exact same result. Now, this is a property only of log functions because we can accommodate that 4 times 4 as a plus log 4 in a log function. What about a horizontal shift? Well, if we take a look at a horizontal shift, well, if I take a look at my graph of y equals x squared, and I can think of the easiest point to keep track of is my horizontal tangent there. It gives me this 0 right here. Well, if I shift the graph, notice that a horizontal shift doesn't actually change the shape of the graph. It does, so all the slopes are all the same, except that at this point here, now that slope's been shifted over. So what ends up happening is I get a shift down here. Now it's the exact same function, but that we just have to accommodate that shift. We have to just keep track of that shift. So if I have a horizontal shift in my original function, as long as I keep track of that horizontal shift, this minus 3 in the original function, just have to keep that track of that minus 3 in the derivative function, and that will allow us to accommodate that horizontal shift. The horizontal shift doesn't change the shape, so it doesn't affect the actual differentiation, but we do have to keep track of that in our derivative. So in general then, the horizontal translation does not affect the derivative. We just have to keep track of it. So here is an example. Y equals 2 tan x minus pi. So if I want to differentiate this, the 2 on the outside has no effect on the derivative. I differentiate the tan, that becomes secant squared. And if there's a horizontal shift, as long as I just keep that horizontal shift, I don't need to do anything else. I know that the derivative is going to have the same function, secant squared, but the derivatives, the slopes are going to be different by a shift of minus, or in this case, plus pi.